Alright guys, so here we are back at it, homework 3.1, part 3. Um, so in number 1, we're going to consider this lemma 1 we proved in class last time. So let me just remind you here what's going on. In lemma 1, what's it say? It says we have these two lines, L and M. So idea here's L, here's M. Right, that pass through this point P, and we have two different points A and B on the line. When I say different, I just mean they're not equal to P. They could be the same point though. So in part A, it says A and B lie on the same side if and only if they lie on the same side of M. So this should be pretty obvious. Right, so A and B here obviously lie on the same side of P, and it's if and only if they lie on the same side of M. We could also switch this statement up in part B, which is A and B lie on the opposite side. So you could have, A here, and now B on the opposite side, if and only if they lie on the opposite side of M. All right, so you have these two ideas, being on the different sides of a point P or being on different sides of the point M, but they're actually the same idea. Okay, even though we say them differently. So that's the big thing, and we're going to get rid of this right here. Yeah, there we go. All right, so in this first problem, what you want to do is use this lemma to prove the line separation property. So we already talked about the plane separation property. We're taking this as an axiom. Right, so this is B4 between this axiom 4 is the plane separation property. We have a similar property for line separation because of this lemma. Really, these are really sort of the same ideas, lying on the side of a point versus lying on the same side of a line. So we want to prove, let's just look at the first part. So if I wanted to prove this first part, part 1, so proof of part 1, and I'm going to go this way, of course, first. So what I'm going to do is assume A and B are on the same side of P, and B and C are on the same side of P. Okay, then what do we know? Well, you can just say, well, then A and B lie on the same side of M. Oh, I guess I need to make a line here. So I'm going to have to add in a statement for this. So why don't I up here make my assumptions? Let's let L be a line. So up here, maybe I'll sort of restate. So maybe I'll say let L be a line and P lie on L. All right. So then, we know there is a line M not equal to L with P an element of L. All right, so P lying on L. And I'm running out of space here, so let me just say, so by, this is actually proposition. I think it's 2.5. You can check it, but I'm pretty sure 2.5 says if you give me a point, there exists at least two distinct lines going through it. All right, so now we let that be the case, then we have that a case. Now assume A and B are on the same side of P, and B and C are on the same side of P. Then we know, and I'll let you kind of finish this up, okay? So then we know what? Well, by lemma 1 up here, we know that A and B are on the same side of M, and B and C are on the same side of M. And so that's all by lemma 1 part A. So our next statement we get all this by lemma 1 part A. Right, and then so once we have that, then we can use the betweenness axiom 4 to conclude that A and C are on the same side of M. Thus, A and C are on the same side of P, again by lemma 1 part A. So after you do this by lemma 1 part A, you're going to say, and by B4 part 1, right, again, we know, right, then you're going to say A and C lie on the same side. Let's erase that. Of M, right? Hence, okay, then you finish it off. Hence, by lemma 1 part A and B lie on the same side of P. Oh, but it'd be A and C, right? So A and C lie on the same side of P. Okay, going the other way is exactly the same, pretty much, right? So now I'm going to assume. So I want to go the other way. I'm going to assume what A and C are on the same side of P. Okay, so A. Oh, I don't have to go the other way. What am I doing? I just want to go back this other way. So I'm just going one way. I'm just proving one, right? So I think I did the same mistake yesterday on the last video, right? So I'm just going if this, then that. Okay, the prove 2. Okay, this is exactly the same, right? So assume now A and B are on opposite sides of P, B and C are on opposite sides of P. Right, then invoke lemma 1, so we know A and B are on opposite sides of M, B and C are on opposite sides of M. Then invoke axiom 4, betweenness axiom 4, part 2, right, which tells us if these two are on opposite sides of M, then A and C are on the same side of M, and then go back and invoke lemma 1 again, and then we can say that A and C lie on the same side. Okay, so that's the idea. So hopefully that clears that one up. And number 2, all right, so let's look at number 2. Okay, so in number 2, this is what we're going to call the order property, really. Right, so any of these betweenness, if we have several betweenness statements and from them we want to decide another betweenness statement, it's really part of this order property. All right, so in the first one, this is the one we did in class. So in the first one, we have A star B star C, and we have A star C star D. All right, so what do we know? All right, so we know on some line, what we have is ABC. So we have A, B, C. And we also have ACD. Right, so we also have this A, C, D. And we want to show, right, what do we want to show? We want to show first in part A, B star, C star, D. So basically you want to show C's between B and D. And the way we're going to do this is you have to pick one of these points, and the point you pick is the thing in the middle. Right, so we want to show B and D are between C. So what you're going to do is you're going to pick this point C, and what we can say, well, we can say several things. The first thing we can say is by assumption, A and B lie on the same side of C. So we know that A and B are on the same side. And I guess in this one we're just drawing the picture, right? So I guess we can leave it like this, right? So this is the picture. And the way the reason it works is that we have A and B are on the same side of C. and this is really by, and this is where we're going to use lemma 2. So this is by lemma 2. So if you have A, B, and C, we know that B and C lie on the same side of A. Or we could rewrite this, right? Or we could say, you know, instead of writing ABC, you could write CBA. You know, so notice that, I mean, this ABC and this ABC are not necessarily supposed to say the same thing, right? We could rewrite ABC as saying C star, B star, A, and then use this lemma right here, and this would say that AB or BA, doesn't matter which one, lie on the same side of C. So that's what I'm using there. So that's by basically lemma 2. And that's part B. And then I also notice here these blue dots tell me that AD lie on opposite sides of C. So, and again, that comes from right here, lemma 2, part 1. You know, A, B, C, if and only if A and C lie on opposite sides of B, right? So A, I know also A and D lie on opposite sides of D. And I'm basically done right here. I just call up, right, line separation property 3. I think I saw somebody in class just write like this, line separation property, right, 3. Right, so by line separation property 3, right, basically we have DA lie on opposite sides. Remember, these statements are symmetric, right? So if AD lie on opposite sides, certainly DA lie on opposite sides. And there's a mistake right here. Erase that. This should be C, okay? And so we have DA lie on opposite sides of C, AB lie on the same side of C, and I then just use line separation property C to say that means then DB lie on opposite sides. Right, so D and B lie on opposite sides. Right, and then call back up lemma 2, right? If they lie on opposite sides, right, then now I have to say that, oh, opposite sides of what? Opposite sides of C. So now I know then C is between D and B. Right, so by lemma 2 part A, we know that we have what, D, or let's do B, right? So B star C star D. Right, that's the idea. I guess if you want to write this up formally, which you can, right, you can do that for part, I think it's what, E? Yeah, for part E we do that. If you look at the next one, part B, so this is the one we did in class. Let's look at the next one. So the next one, part B, we have the same assumptions. We have B's between A and C, and again C's between A and D. And so our picture looks like this. We have our A, we have our B, we have our C, and we have our D. And what do we know? We know that we have these 3 points here, right, that lie between each other, and we have these 3 points here that lie between each other. So C lies between A and D. And we want to show then, what do we want to show? We want to show that B lies between A and D, right? So we want to show basically, we want to show this. Okay. And so what can we do? To do this one, we can use the last one, right? We know. Right, what do we know? We know that C lies between B and D. Right, so we know this. We just proved this in the last problem. Okay, so I know I have this. Right, so I can choose my point, and the point I choose, right, of course, is going to be B. Right, so I'm going to choose this as sort of my reference point. Right, so I know this, and of course I want to show that B is between A and D. And the way this one works, you can look at it here. The way this one works is that I know what? Okay, so I know from the last problem that C and D are on the same side. And I know from assumption, right, these right here on opposite sides. Right, so I have A and C on opposite sides, C and D on the same side. And so, again, I invoke this line separation property 3, which tells me then that A and D will be on opposite sides. All right, so this will allow me to say A and D are on opposite sides of B. And then I apply this lemma part 2. Right, so this tells me, right, after I know this, I apply lemma part 2, and then this will tell me certainly that B is between A and D. All right, so if you know they're on opposite sides of a point, you know that the point itself is between those other two. And that's it. All right, let's look at the next one. And in these, you're just supposed to draw the pictures. I'm just explaining the proofs as I go along. So I'm kind of doing part E as I do all these. And you just need to choose one for part E. Right? Part E says use your picture and prove one of the above. But I also want you guys to see each one here. Okay, so again, I have the same setup. I'm going to get these 3 points, or 4 points. And this one, they're going to tell me, again, A, B, C. So I have this, A, B, C. And then they also tell me, I guess we should write it up here, right? So I have A star, B star, C. And I have what else? B star, C star, D. And for this one, I need to write this one down. Let's write B star, C star, D down. So I have B star, C star, D. And I want to show, what do I want to show? I want to show that B is between A and D. So I want to show that I have this. And the way this works is, again, I'm going to choose B to be my sort of reference point here. And what I can say, obviously, look, A and C are on opposite sides of B, whereas C and D are on same sides of B. So again, by this line separation property 3, I can conclude that A and D are on opposite sides of B. All done. I'm going to let you do D on your own, right? But it's the same sort of setup. And then you can, just try to do what we did above for that one. And then pick one to prove, whichever one you want. Okay, so that's the first side. The second side, over here, we're going to prove Pasch's theorem. You can always look this up in the book. There is a proof, and you can kind of use it as an outline. I'll try to get you started here. So if I want to prove Pasch's theorem, what I need to do, let's just write down Pasch's theorem. And the proof, right, you should probably copy down the statement. And in fact, it says first, let's draw a picture. So let's do that first. Let's draw a picture of this, because the picture, once you see it, is sort of obvious what it's saying. So it's saying A, B, and C are distinct non-collinear points, and L is any line intersecting the line segment AB and a point between A, B. So you have a point A, you have a point B, and you have a point C. And you can draw a line segment here. Here's AB. And then there's a line L. Right, so here's my line segment L, intersecting AB, and it says it intersects at some point between there. Who knows what that point is, but it intersects AB at some point. Great. And then the conclusion is L intersects BC. Right, so here's the line segment BC or AC. All right. So it intersects one of these. And furthermore, if L does not lie on C, so if it doesn't intersect at C, then L does not intersect both AC or BC. Okay, so for the proof, so this is part A. You draw your picture. And then for part B, the proof. All right, so you're going to make these assumptions. So again, make your assumptions. So assume, assume what? Assume A, B, and C are distinct non-collinear points, and L is any line intersecting the line segment AB in a point between A and B. Right? And then what? Okay, so what you know. All right, so after you make this assumption, period, whatever. So you have a period here. Then what? Then we have two cases to consider, right? Then we have two cases to consider. All right, case one. All right, case one, C is on L. All right, and then case two, C of course is not on L. Right, one of those two things is going to be true. If you have a line L, either C is on it or C is not on it. All right, so case one, if C is an element of L, then C is an element of the line segment BC, and actually C is an element of the line AC. So you're done. Right, you've shown this that L intersects AC or intersects BC. So now we can assume. So now assume C is not on L. All right, so now what we want to show, we want to show C is an element of the line segment AC or C is an element of BC, but not both. So it's an element of one or the other. And the way that we do this, let me just get rid of this, right? So the way that we're going to do this is actually real simple when you look at the picture. When you pick your point C, right, it either lies on the same side of A or on the opposite side of A. Or if you want, you can do it with B. It either lies on the same side of B or the opposite side of B. So there's just a choice here. So I'll just make the choice that we'll do with respect to B. So we assume C is not on L. We want to show that C's in here or C's in there, but not both. So notice, let's just write notice. C and B are either on the same side of L or on opposite sides of L. And then we'll do each case, right? So if C and B are on the same side of L. What can we say? So if they're on the same side of L, then we know what? Well, then we know, and you can just look at the picture because we know A and B are on opposite sides of L. So we know A and B are on opposite sides of L because AB bar intersect L. Well, let's just do it because P is an element of AB bar, right? The line segment AB, right? And if you want to try to justify this further, you can. I mean, if you look at the homework, which I closed, so I have to reopen it. But if you look at the homework, okay, it's going to tell us. It's going to tell us what? It's going to say, tell you what. It's going to tell us that P, right? What's P? Right, P is this point that is on the intersection of this thing, right? So P is this point here that's on the intersection. Oh, I guess I have to define that. I haven't defined that, okay? Because P is an element of AB bar where, I guess that's just from the picture, right? Where P is it's a point is P where P is the point on L that is between A and B. All right, I guess I need to say that. And that's all from assumption up here. All right, so you're going to assume, you assume all this stuff, and so you could actually put P up here. You could assume, all right, so assume A, B, and C are distinct linear points, and L is any line intersecting A, B in a point, and you can put here P between A, B. Right, then you don't have to say where down here if you don't want to, but you should be okay. Okay. So I know, I have C, B are on the same side, A, B are on opposite sides, and these statements are symmetric, right? So if I want, I could say, A, B are on opposite sides, B, C are on same sides, right? And then I call up, again, go back over here, opposite, same, okay? And so then what do I have? Well, I have AB and CB, so I have CA are on, right, the same or the opposite sides, right? So thus, you can say A and C are on opposite sides of L. Right, hence, right, what does that say if you're on opposite sides of L? Hence, AC intersect L is not equal to the empty set. Right, and I believe that's it. All right, that's so not equal to the empty set. And now I just realized there's a mistake up here, right? So I should have, this is not C. I don't know why I have C there. I don't want to show that. Okay. What am I really trying to show here? I mean, I proved what I wanted to really prove here, but I really want to show that L intersect AC is not equal to the empty set, or L intersect BC is not equal to the empty set. That's what this picture is saying. I got caught up with that C for some reason. All right, so I want to show that this line crosses that line, or this line crosses that line, if it doesn't cross C. Right there. So hopefully that didn't confuse you. too much. But I don't really want to redo this. So we're going to stick with that. All right, so I have one more case to consider. Right, so this one was if C and B are on the same side. Now we have the second case. Now what if C and B are on opposite sides, right? So let's notice C and B are either on the same side or on opposite sides of L. So maybe let's extend the page here, and then we'll say, okay, now if C and B are on opposite sides, right, then what? All right, then we still have blah, blah, blah. All right, so we still have what? So you can come up here, then we still have A and B are on opposite sides. And so if you know that basically A and B are on opposite sides and B and C are on opposite sides, then we should have what? And so you think about that, and then you can finish off the proof of this. Notice also here, we showed this is not empty. Basically, we said if AB are on opposite sides, which means up here, sorry, CB are on the same side. So, and this basically says what? This says if L intersect BC is equal to the empty set, then we find that this is not equal to the empty set. And here, if we say C and B are on opposite sides, which means basically CB, the line segment CB intersect L is not equal to the empty set, then we'll show, right? You'll show here that the other statement, a C bar intersect L, is equal to the empty set. And you'll be done. All right, so kind of follow that as sort of your guide, and you should have a proof at the end of Pasch's theorem, which really says something that we kind of know intuitively, which is if you give me a line segment and a line goes through it, and I have these three collinear points, then this line either goes through the point C or intersects one of these line segments, BC or AC, in exactly one spot. Okay, let's look at the last problem on the homework. Okay, and so on number 4, we want to finish up. We want to look at our first example of a model that satisfies both the axioms of incidence and betweenness. A model that satisfies both of these axioms would be called an ordered incidence model. So the model we want to consider is the Cartesian plane. And so I give it to you here. Here's S. It's all the points in R2. And L, of course, are just the lines in R2. And we see here the way that I've labeled them as L sub A, B, and C, where A, B, and C are real numbers, and not all of them are 0. So one of them can be 0, but not all of them. And then I explain to you, what these lines are here. So this is an example of an ordered incidence model, and we're going to do the following in your journal. So in your journals, you want to sort of write some of these things down. Let me pull this up again. All right, so you want to draw a picture that illustrates betweenness, B between A and C in the Cartesian plane. Hint, there are actually 2 different pictures that you need to draw. So think about this. One picture is real easy. It's just a line, like this. If I have a line L, what I mean by something being 3 points with 1 between, it's just like this. Right? I have A, I have B, and I have C. So I'd say B is between A and C. But there's actually another line you can draw, right, where you're going to kind of be in trouble, because think about what you really mean here. What do you really mean by A being between B and C? So if you label these points like this is A1, A2, right, these ordered pairs, and this is B1 and B2, and this is C1 and C2. And in part B, you're going to explain, what does it really mean for B to be between A and C in the Cartesian plane. And so if you think about this, what does it really mean when we say B is between A and C? And the way that I drew this picture, I really don't care about A2, B2, and C2. What I really care about is A1, B1, and C1. So from this picture, if this is my line, what I mean by B be between A and C is really A1 is less than B1 is less than C1. And you can kind of convince yourself, but there's one picture that you're going to be in trouble. Right? So there's one type of line that's going to get you in trouble, and so that's what I want you guys to try to draw over here. And then part B is halfway done. What do you mean by B being between A and C? And you can look in your textbook on 117 and 118. One version, if you give me 3 points on a line, looks like this. All right, so this is one version. And then there's a second version, right, depending if your line is drawn a certain way, and if it's that version, you have to do something else. And then in part C, explain why the Cartesian plane is an ordered incidence model. In this part, I just want you guys to think about, why does it satisfy I1 through I3 and B1 through B4? So just write maybe a sentence for each one, like I1, or a picture even, so it's clear that you understand, sort of why the Cartesian plane satisfies the axioms of incidence and satisfies the axioms of betweenness. Okay, so I hope this didn't confuse you too much. I know on number 3 I did kind of a sloppy job, but I really don't have time to go back and redo it. The proof is in the book, and so you can look there for some hints. But I think if you look at what I did and you write it up in a better way, better than the way that I wrote it, it should be clear. All right, I'll see you guys on Monday.